Hello students, so welcome to graphing exercise for Physics 215. We have already seen and we have already learned a few tricks as in how to plot data in MS Excel in basic introduction to plotting data using MS Excel in a previous video. Now we are going to use what we learned there and apply that to this lab. So this is more or less the roadmap that we will follow here. But let's first see what we are dealing with here. This is the lab manual. So please read the lab manual carefully. Your page 2 in the lab manual tells you about straight lines, how you deal with the slope, and sometimes you'll have to apply some sort of mathematical transformation to these equations so that your data, when you plot it, becomes more or less linear. And wherein it is linear, that's when you can apply a trend line to explain the behavior of the data. If the data is not exactly linear, it still follows a linear trend, and you're trying to capture that linear trend using a straight line. It's an approximation, but this is often used in scientific studies, and that's what we will use in this lab. Now there are so this is our first data set. This is already in linear form, so nothing much to do. This is a second data set, and you can see you're given n and lambda, and these are 1 over lambda and 1 over n squared. So of course this is not in a linear form, and so we'll have to do a mathematical transformation so that this becomes linear. Then data set 3, we have an exponential function, exponentially decaying function. So as time increases, the value of v drops. So of course this is also not linear. Note that here you're told to plot this on a semi-log graph paper. You don't have to do that because we are directly plotting that using MS Excel. And when you plot using MS Excel, you're essentially doing something equivalent to plotting on a semi-log graph paper. Okay, and number 4 is where you're only supposed to plot. Just plot n and lambda, and there you go. You don't have to apply any kind of mathematical transformation or adding a trend line to it. So, summarizing, dataset 1, 2, and 3 will plot the data such that it is linearized using a mathematical transformation. And when the data behaves as a linear-ish data, we apply a trend line, a linear trend line, to explain the behavior of the data. And when we apply a linear trend line, we will get an estimate for the slope and intercept, and we use that to answer the questions over here. For instance, in dataset 2, you're trying to find out the Rydberg constant R. In dataset 1, you're trying to find out the EMF, the script E, and the internal resistance, the small r. In dataset 3, you're trying to find out the time constant, tau, which is equal to the resistor used in the circuit, its resistance, and the capacitor's capacitance C. So RC is the expected time constant. However, when you use the data, you will probably find the value of tau from data fit somewhat different from it, but it should be very close to this RC. Anyway, we'll go over this later on again. Now let's look at what we have here. So first, of course, read the lab manual for instruction. Then there are these 4 data sets. For the first 3, you will apply a linear transformation. So you'll recast the model equation into a straight line equation, which is what we are calling a target equation, and then identify the independent variable, which is x, and the dependent variable, which is y, in that target equation, and then also identify the expressions for slope m and intercept c. So this is where we are talking about an equation given to us, and we are transforming that and then identifying what is our slope, what is our intercept, which is x and which is y. Once we have this, then we plot x and y, and then we add titles, axis labels, units, legends wherever applicable, and finally for dataset 1, 2, and 3 we add a trend line as well. And when we add a trend line, we do make sure that we have the equation of the straight line fit and also the r squared value of the fit. So r squared is actually a goodness of fit. It tells you how good the fit is. It ranges from 0 to 1. The closer to 1 the value of r squared is. For linearly distributed data, if you fit a linear trend line, the higher values of r squared explain that it's a good fit. Okay. Okay, and yeah, any other specific instruction in the data set, do follow that. So now that we have talked about this, let's go and take a look at what we have here in this manual. So I'm mostly focusing on the second page of the manual. This m equals y2 minus y1 over x2 minus x1. This is the slope. y2 and y1, you just pick any 2 points on a straight line, and the corresponding y and x values are y1, x1, and pick another point somewhere else on the straight line, call that y2 and x2, and then just find out whatever this is. That's basically what the slope is. However, when we use the straight line fit, we are using a lot of different data points, and so we don't do this. We can always find out the slope from a data point, but since you're not using a graph paper, so you don't have to use this formula for that. This is only necessary when you're using a graph paper. The Excel will actually give you the calculated value of this slope. So, yay. Okay. So now, when you have a linear form like this, so for this v equals ir equals script e minus I small r, this here negative r is like the slope, I is the like the x value, and this script e is like the constant c. So we have already talked about this. Here is your straight line, y equals mx plus c. M is your slope, c is your intercept, x is your independent variable along x-axis, y is along y-axis. So we have to identify this for each of the data sets. So for instance, for data set 1, we have v equals ir minus script e I over r, and we can rewrite this in 2 different ways. Option 1 is we write this as v equals epsilon minus ir, where this r is small r, and note that this capital R here has nothing to do with our r squared. That r squared is a name for a statistical measure. It has nothing to do with r. This capital R is the resistor's value in ohms. Okay, so you write this equation like this, you identify which one is v, y, which one's x, and which is m and c. And when you do that, then you can go ahead and plot them accordingly. The other option is you write IR equals epsilon minus I small r, and then you transform this as capital R equals this, and finally you can identify that capital R is your y, 1 over I is your x, epsilon is your m, which is the slope, and negative r is your intercept, the constant c. So if you plot r versus 1 over I and fit a straight line, then the intercept of the straight line would be negative r, and the slope of the straight line would be this script e. And this script e is, so the slope will give you the EMF, and the negative intercept will give you the internal resistance. Okay, great. Now the data set 2. For data set 2, you can express this in two different ways as well. One is, we note that if you write 1 over lambda as y, r as our slope, and we call this 1 over 4 minus 1 over n squared as x, then obviously in this model the intercept c becomes 0. So this now becomes a constraint in the model. We are choosing a model where our intercept is 0. You can plot, you can of course plot this data. You can calculate what this 1 over n squared is and 1 over lambda is, and then can calculate 1 over 4 minus 1 over n squared for x. And once you have x and y, you plot them, and then apply a trend line to it, a linear trend line, just like here. Format trend line linear. And perhaps you would remember in an earlier video I have shown you already how to add a trend line. So you do that, and when you do that, additionally you also want to set this set intercept. This set intercept equals 0. We are choosing to do this because in this model our intercept is 0, and so we have to enforce that constraint if we want to use this model. However, if instead of using this transformation, if you just change a little bit in option 2, 1 over lambda equals minus r times 1 over n squared plus r over 4, you can see that we can call 1 over lambda as y, 1 over n squared as x, negative capital R as the slope, and capital R over 4 as the intercept. In this case, we also apply a standard linear trendline fit, but we do not set an intercept, because in this case we already do have an intercept, r over 4. Okay. All right. Just to know what Rydberg constant is, the value you expect, it's about 1.09678 times 10 raised to 7 per meter. Okay, so the straight line fit that you do hopefully will give you a value very close to this, but you're using this data, so whatever this gives you, that gives you. But this is just to know that this is a value, and this is the source on Wikipedia. Okay, so now we go on to the next one. So in this case we have an exponent on the right side but no exponent on the left side. So we want to write this such that we get rid of this exponent. Okay, and whenever you want to get rid of an exponent, you apply a logarithm on either side. So this is what we are doing here. Natural log of v on left side means natural log of whatever was on the right side, and when we do that, this is a multiplication of v naught times e raised to negative t over tau. Your tau is RC, And so we can write this as natural log of E naught minus t over tau, because natural log of E is 1, and this is essentially the set of rules applied to this. Since this is not a class where we want to go in depth over natural logs or logarithm, so I'm not going into much detail. If you have questions, of course you can ask the TA or the instructor who's teaching you, but I will also suggest, if you have questions, if you have previous material on any logarithm, how to apply logarithm, go over that just to quickly brush it up. But for now, if you just know that this is a transformation, that should serve your purpose. Okay, so now this natural log of V equals negative 1 over tau times t plus natural log of V naught, and we identify which one is y, x, m, and c. Okay, great. And what is the expected value of tau, which is the time constant? That is R times C. R is 100 kilo ohms and C is 330 microfarad. Micro means 10 raised to negative 6 and kilo means 10 raised to 3. Okay, so keep that in mind when you finally calculate RC. It should be as ohms times farad, which should give you which essentially means just seconds. Ohms times farad is seconds, because this is T over RC, and anything exponent and any power of exponent has to be unitless. So RC, R times C, has the same unit as the time T, and T is in seconds, hence RC, when you multiply, the unit of that would also be seconds. So the kilo and micro, those are essentially just shorthands for writing 10 raised to 3 and 10 raised to negative 6 respectively. So you'll end up getting an ohms times farad as the unit, which is equivalent to seconds. So keep that in mind when you multiply this. People make mistakes, just know for a fact. Okay, so yeah, you apply that and know for a fact that in this case the slope is negative 1 over tau. So once you have an estimate of the slope, when you plot natural log of V on the y-axis and the time t on x-axis, and then apply a trend line to it, the slope that you get, equate that to negative 1 over tau, and then you can estimate what the time constant tau is. Okay, and then you can compare with the expected value of tau. Okay, the last part, which is fairly simple. You have wavelength lambda and you have refractive index n, and you just want to plot your refractive index n on the y-axis and wavelength lambda on the x-axis and show the plot. Okay, so that's basically all you have to do in this case. So we'll stop the video here, and now we'll go and the next part of this video will show you a few things for plotting the data and applying trend line. So we have gone over what we need to do in the graphing exercise. However, there are a few things in your lab manual which would be nice to go over a little bit. For instance, if you have an equation y equals a times x raised to n, where x raised to n, this is an exponent. And so whenever we have a power of something, you'll take a log of this on either sides. And what happens is when you take a log, the left side will be log y, the right side would be log of a plus log of x raised to n, and the power comes in front and that gets multiplied to log of x. So when you have an equation like this, where you have log on the left side and log on the right side. We call that log. But instead of a x raised to n, if you had y equals a times e raised to negative x, this is somewhat similar to dataset 3. And you take a natural log. A natural log essentially is nothing but log base e. So whenever you take a log, it has a base. It could be 2, it could be 10, it could be e, it could be 20, it could be 8. It has a base. Generally, we take a log base e, and as a shorthand for that, we write ln. And there could be log base 10, there could be log base 2, or there could be log base anything else. In Excel, you would see that the log base e is ln. There is a log 10, which means log base 10. And there is another function which is log, which is to calculate logarithm to base anything. So that a generic function. For your purposes here, you will be using natural log, which is so the function in this case is capital Ln. Okay. So this is what you have more or less in your dataset 3, and that's the kind of transformation we are using in this lab. So now we will look at the plotting for dataset 1, and once we understand what we have to do that, we'll essentially have to do that for dataset 2, 3, etc. I'll show you a little bit what you need to do. I would not use the exact data as you have in your lab manual. You will have to look at the data here, and you have to read them. You have to take them out from here and manually paste in the Excel. Make sure you do not make a mistake. It's fairly easy. Go over it carefully and put it in. And you do this for dataset 1, 2, 3, and 4. Now, once you do that, then you'll calculate the quantities which we have identified already as x and y for these data sets, and then we plot them. For dataset 1, I'll suggest you use option 2. For dataset 2, I'll suggest that you use option. So this is dataset 4. So dataset 1, use option 2. For dataset 2, also use option 2, because then you don't have to worry about setting the constraint for equals 0. And then dataset 3, there's just one option, use that. Okay. Now getting back to these data sets, yes, I will take some of the data points from here, but then while showing this in Excel, I will just take a value somewhat different from your values over here. So my plots would not look exactly linear, but just to give you an idea what are the steps that you need to do, I will show you that. So please do not look at what I have in the Excel when I show you in the video and answer from there. You are supposed to plot your data from here by reading whatever is there on the manual, and then you follow the process. You follow the process as I showed you, but you take the data from here, and then the result that you get from there, you use that to answer any quizzes or to prepare your Excel workbook. And if you're supposed to submit your Excel workbook, then you use that data for that. Okay. All right. So now we'll go and look at the video for how we work with the data. Okay. So what do you want? So if you have, let's see. So for the first one here, if you want 1 over I, or where are they? Yeah. So yeah, so this one. So here our x is 1 over I, or y is capital R, right? So we are going to look at, so our x is, instead of x, let's just write down 1 over I. So we already have I. Alright, let's first write down as the data is given to us, I, and then v. Just to make things modular, I would say you insert 2 more columns, and then this is resistance current voltage, and then this is volts. So this is the row for units, then this is amps, and this is ohms. Okay, and then you can go here and write down whatever the values of resistors they were used, all the way to 10. And I'm not going to fill up these values here for you, but yeah, so whatever the value of I is. For the time being, just to dummy fill, I'm just going to write down this times 10. Just note, I am filling in the data just for the sake of filling in data. This data is not the same as the data you have. You should be filling in the data from the lab manual. Okay. Okay, so now what we have, now what we want is our x. Our x is, we want x and y. So our x is 1 over I. So this is 1 over I. And this is R. Okay, so this is equal to 1 over I, and then y is equal to just a reference to our resistor, and then you take these two and then drag them down. Alright, if you want, you could also have like 1 or 2 digits like that. So this is called a format painter. You can paint the same format everywhere, but yeah, this is not an Excel class, so if you need to know anything, just Google. Alright, so what do we have here? So we have x and y, and if you want to plot this, you'll go to insert and then make a plot. Okay, so yeah, so obviously when we plot it like this, this is not a straight line, and what we have here, this is not a straight line because I dummy filled data. When you take your data and then apply a straight line to it, it'll be whatever it is. But you can also test this with the, just a second, you can also test this with your option 1, which is here. Yeah, so you can also test the same thing with option 1 similarly and see what you get for these slope and intercept, and then you can figure out what your internal resistance and the EMF are. Okay, so that's the idea for the data from 1. For 2, we are supposed to plot 1 over n squared as x and 1 over lambda as y. So that's basically very simple. So we go over here and create a new sheet, and let's name these as like part 1. Then the next sheet we'll rename that as part 2. All you have to do is right click on it and rename, and that lets you rename. And we'll have similarly 2 more sheets, and you can go ahead and rename them as part 3 and then part 4. Okay. So part 2, in this case you're supposed to write down the number. So I'll start from the 3rd row, n. I'm just going to write down n and lambda. If you want, you can also add the column for color. And then whatever it is, which is number, and it doesn't have, a number doesn't have any units, so nothing there. The wavelength is nanometers, and this is wavelength. And instead of writing that script lambda, I'm just going to call this lambda. Okay, and then you can just fill up 3, 4, 5, 6, 7, 8, 9, and note that this infinity, your infinity is a very, very, very large number. Now infinity is infinitely big compared to any other number. So can you plot something like that in MS Excel? No, because MS Excel is only plotting a finite set of numbers. We cannot plot infinity. But we also want to show a number which is very, 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 very large when we are looking at also these numbers like 3, 4, 5, which is basically under 10. So numbers under 10 and something very, very, very large, which is infinity. So to assess or to estimate infinity, let's just put a very large number, and I'm going to write that with a formula and make that as 10 raised to the power of let's say 12. Okay, I mean, of course 10 raised to the power 12 is not infinity, but when you consider that with any of these numbers which are like under 10, 9 is like more or less 10, so 10 raised to the power 12 is 10 to the 11 times bigger. So it's like 100 billion. It's a lot. So that's the idea. Okay, so when we do that, now you can go ahead and fill in the values like 656.3, 4, 8, 6.1, and so on. But when you are calculating x, so there comes x, and there comes y. An important thing is when you calculate here, then Rydberg constant is in terms of meters, like 1/meters, but it's in meters, not like nanometers. So your units here, x is for us is 1/n squared, so this is 1/n squared, and y is 1/λ. Okay, so what is 1/λ? We want y to be 1/λ is we want it to be 1/meters. Okay, and since n is a number, so 1/number squared is also a number, so x doesn't have any units. Alright, so we will, for x, this will be equal to the value there, not that, so 1/, and then I always prefer to use a parenthesis, so we absolutely know what we are squaring. In this case it wouldn't matter, but I'm gonna use that anyway. Saves you a lot of trouble and a lot of times. Okay, so let's set this to okay, and now our y is 1/λ. I'm just gonna change. I'm also dummy filling right now. Okay. Then these are not the actual values that you have there. Just to do this quickly, I'm filling up something. Then okay, so now that we have that, let's quickly calculate what 1/λ is. So 1/λ. And if we do this, that's not exactly what we need. See, the thing is, our lambda was in nanometers, right? So we have lambda, so everything here has that times 10⁻⁹. So what you need here is this times so whatever you have here, that times 10⁻⁹. So that's the change that you have to do here. So it's now in meters. Okay. All right. So now we have this. Great. And since we have x and y, we can go ahead and insert the data. And you see it kind of follows a linear pattern, because whatever I dummy filled, that was kind of similar to the original data, which is why it's not terribly bad. And you can also go ahead and add a trend line. So click on this, more options, and linear, but you also want to show these. Okay. And when we do that, this gives us this thing. Let's make it bigger. I'm not gonna write down the title for the chart or the X and Y axis labels. Any units used, I'm going to leave that to you. You do it right. If you're being graded on that, you're fine. If you leave out units where you're supposed to write them, you'll probably lose points. But this is an important part, that in order to transform this from nanometers to meters, you have to take care of that conversion, and you have to multiply it by 10⁹. Alright, so when you do that, you get this, and then this gives you this result. And we know that this 10⁷7 is actually the value of your Rydberg constant, but this quite doesn't give you the actual value of the slope, which is why when I showed you earlier, slope and intercept, what you want to do here is write down slope, and then you want to select the values of y's, and then you want to select the values of x. Note once again, whatever you see here, the values of y are not the actual values of y. So once again, please do not answer from here. This is only for the purpose of showing you what the steps could be, but you need to work with the actual data. Alright, so here is our slope. Yeah, it is right. So this is our slope here, and I'm just going to copy this and then paste it there, so I don't have to change everything. Intercept. Okay, and this is our intercept. Quickly, if I want to check, I would check that the intercept times 4 minus the slope. No, not minus. Intercept times 4 plus the slope should be very close to 0. Now this is not very close to 0 because the values that we used, they were different, but if you do check this, which is intercept times 4 plus the slope, this should be very, very close to 0. That's because of the design of the model. Look at option 2, model, and you'll know why I'm talking about that. Okay, so we are done with that. Now let's go back to here, and now let's look at dataset 3. So for dataset 3, it's fairly simple. You take the time and the voltage and plot them, and our x is time and our y is natural log of the voltage. Okay, so let's get back to the Excel part 3. So we have t, which is time in seconds. We have millivolts, which is our voltage, and that's for V. Okay, and then you'll go ahead and write down these values. which essentially increase by 5. So I don't know if you select this and drag this down if that'll do it or not. Oh, it actually does. So you can go all the way to 90, and then you can take these and write them down. So 830, 743, 656, 580, 513, and so on. So I'm just gonna dummy fill from here onwards. Oops. Alright, so I was trying to get a value kind of similar to like that range, 103. So I just decided to subtract 30 from each previous value, but this is not the original value. You can see that I'm dummy filling for the sake of quickly being able to show you more or less what are the important steps for you. You must work with the original data that's given in the lab journal. Okay, so our X and our Y. Our X is just T. Oops, yeah, our X is T, and our Y is ln V. All right. Yeah, that's pretty much it. So when we do this, instead of, so we can say that X is equal to T, and just like earlier you had millivolts, you want to write that down in terms of volts. Not that it would matter, whatever you do here, that'll be the same units for V naught, but let's just multiply accordingly, so we end up getting V in terms of volts. But know for a fact that you are always dividing anything inside a natural log or a power of an exponent. Any of these things will never have something with units. So when we are writing V, what we are doing is we are dividing V by its own units. So even if it is 999, shouldn't matter. Okay. Alright, so now what I was talking earlier is that you can write ln. So see, if I write ln, that says returns the natural logarithm of a number. We are going to test this with another function, which is exp, which is exponent, which is e raised to, and if you write down 1, this is natural log of exponent raised to 1. That should be essentially 1. So this is a litmus test for us, and that's right. If instead we did log, so if you do log, you have to also specify the base. If you forgot what logs are, logs always have a base. So when you say just log, it's normally log 10, but you also want to calculate log base 2, log base e. Log base e is natural log, that's ln. So if you did this and then did exp1, that will not be 1. So this is what I was talking about earlier. Alright, so now that we know what to use here, so we'll just do ln of the v. Alright. And that fills this up, and now we can select this, go to insert, click on this and plot. Now this is more or less linear. You can go ahead and add a trend line, more options, and display equation, and we bring this here. We'll make it bigger. Okay, so these are equations here, just for the sake of being thorough. Let's also calculate them using the equations. So known y's selected, known values of x selected, done, and then intercept, known values of y, known values of x. Okay, so you just have to do this, and then you can see that this is the same value as that. And when you do that, the value of the slope is this. Now I won't tell you what you have to do. You'll have to figure out by looking at the expression of the slope for dataset 3, and then you have to infer what would be the value of tau, and then you can compare that with the expected value of tau, which you can calculate by multiplying R times C. R and C. R is the resistor used and C is the capacitor. And yeah, so I'll leave it to that, and whatever you're asked in a quiz or any assignments, you can answer to that. I think this is covered quite well. So yeah, so what did we cover here? We looked at how we recast dataset 1, 2, and 3 into a linear form and then plot that data. We created different sheets for each of them, and then we plotted them. And for part 4, you just want to go ahead and take the data from this table. This should be actually just 2 columns because of less space. This is the same column running, so make sure that you have just 2 columns in your Excel instead of 4 like this. So all the lambda in first and then n in the second. So in this case, your lambda is your x and n is your y, so you just have to write this down and make a plot, and that's it. So that plot will go to part 4. And when you have this, please do make sure that you're saving as you progress through making the plots. And once you're done, yay, you're done. If you're supposed to submit your work in Canvas, do that. If you're supposed to answer questions in a quiz, look at this and do that from there. But I think we have covered almost every aspect that you will have to go through, and all the best.